I am really glad to present Rick Schlichting. Rick is Executive Director of Software and Distributed System Research at AT&T Labs. He was a faculty of University of Arizona from 82 to 90, don't count, yes, too many, for me too. He spent a sabbatical in Japan. So, and I know that Rick continues to go very frequently to Japan. He's very active in the field of dependable computing and for torrents. He's chairing the IFEEP working group since 6-7 years now. And he was also the CC chair of the IEEE Computer Society on the Technical Committee on Dependable Computing and for torrents. His main interests are highly dependable computing, distributed systems, and networks. And I know since few years you moved towards cloud computing, and we will help us know more about cloud computing, I hope, at Extreme Cloud, and we will learn about Extreme Cloud. So, and thank you for accepting this invitation to contribute to this conference.
So I'm really happy to be here to talk about Extreme Cloud. So about a year ago, AT&T Research started a process of defining with the people in our business units 7 research initiatives, or big bets as we call it. And so one of those is Extreme Cloud, and I'm here today to really talk about that one, as well as to talk especially about some of the dependability challenges. I'm not going to focus initially on that. So what I'm going to do in this talk is first tell you about some of the motivations that led us to define this Extreme Cloud initiative, talk about what it is, talk about some of the research challenges, and then depending on the amount of time I have left, I'll talk about 1 or 2 research projects that, although they're not part of the Extreme Cloud initiative because they preceded that, these are initiatives that are dependability related that in fact led in part to the way we define Extreme Cloud. Okay, so before I get started, this is what the lawyers make me put up, and basically says that you can't count on anything that I say coming out as an AT&T product or service at any time in the future, and that we can change our minds whenever we want. I also want to give special thanks to Mary Fernandez and Kate Krishnan. They're the 2 other individuals, along with myself, who are the leaders of this initiative. A lot of what I'm going to talk about is based on their input, as well as the technical team at AT&T Labs. Right? So it's not just me, I'm really sort of representing a much larger group. So we'll get started with trying to answer a very simple question in some sense. What should the next generation cloud ecosystem look like? It's a seemingly simple question, but the problem is there's a lot of semantics buried down in it, and you have to sort of dig in to understand what that means. So for example, very simply, what is cloud computing? What do we mean by cloud in this case? Well, an interesting aspect is that at AT&T, I've been there since 2000, as Carmen said, we've been using the term cloud at least since I've been there. Right? To us, something in the cloud is anything that you access over the network and that you can logically view as being in the network. All right, so we're meaning cloud in that sense, but we're also meaning cloud in the more modern sense, if you will. Network accessible, but also based on virtualized platforms, whether they be virtual machines or open model, we're moving toward virtualized networks as well as all of the opportunities and challenges that entails, right? As far as being able to do dynamic reconfiguration and things like that. All right, so when I talk about cloud, I'm going to talk about network accessible storage, computational resources. I'm going to include the network resources in that as well, and also try to keep in mind that we're talking about a virtualized platform, and also something that we're trying to come up with a general solution. Okay, so that's cloud. That's one part of it. Ecosystem was a term that we very carefully chose. AT&T is an infrastructure company, right? We run big networks, we run cloud offering, and so it's tempting as an infrastructure provider to think about it only from an infrastructure point of view. But an ecosystem means all the way up the stack, looking at things like how do you develop applications for a cloud infrastructure? How do you manage a cloud infrastructure, as well as how do you build it? All right, so when I say ecosystem, I'm meaning everything all the way from the bottom to the top. Next generation. So we aren't starting with a clean slate design. So next generation is supposed to imply that we're starting with what we have, but we really want to push the envelope. Look and see, we're a research organization, look and see what we can do as far as developing a next generation cloud ecosystem. But not from a clean slate design. We're not throwing away everything that's there. We're trying to envision a path from where we are to where we're going in this kind of research. And then this is really parsing it very carefully. So the question, what does should mean in this case? Well, I very explicitly said should rather than will, because we're not trying to predict what the next generation cloud ecosystem will be. We're trying as researchers to influence it. So we're giving our view of what this system should look like. So that's really diving deep into a very simple question. But the answer that we came up with is something that we call extreme cloud. And the term is supposed to evoke this notion of sort of living on the edge and being pushing the envelope as far as what you can do with this cloud. And that's the kind of thing that I'm going to be talking about today, is what that exactly means. Now, part of the problem when you do this kind of research is you have a chicken and egg problem. And it's a chicken and egg problem in the following sense. Do you start from the bottom up? In other words, do you envision, as researchers, building the best, highest performing, whatever qualities you're looking for, infrastructure, and then have sort of the build it and they will come attitude toward what the applications are that will be built on? Right? That's a tempting way to do it. But it's also valid to look at it from the top down, where you try to envision what kinds of services and applications you might want to build on a cloud infrastructure, a general cloud infrastructure, and drive it that way. Now, of course, the reality is it's really iterative, right? So you use these to inform one another. And so you end up doing this kind of iteration in order to break yourselves out of this chicken and egg kind of dilemma. Now, one thing I'll point out now is that none of these, I think, will be exceptionally surprising. And in fact, a lot of these are out there and available and implemented. But they're available and implemented on infrastructures that are very custom. Right? So one example is gaming, online gaming. You can certainly do online gaming now. But if you look behind the curtain at how those are implemented, they're very, very specialized infrastructures. And part of what we're going to do in this research is look at what can we do on a general platform that you might repurpose between gaming and some other use. So let me go through a few scenarios. Right? So there's our cloud on the left. So the first scenario is what we call multimodal interfaces. And I should add that, as I mentioned at the beginning, we've defined some of these research initiatives, these 7 big bets. A lot of what I'm going to talk about here are parts of the other initiatives. Right? So there's this cross-fertilization among these research initiatives. So what's a multimodal interface? A multimodal interface is an interface where you use more than just typing to interact. Right? So for example, the most common one that you might think of is speech. Right? So you can now, using Siri and other tools, interact with phones, for example, using a speech interface. So how do you implement that? It's not implemented on the phone itself. The speech processing requires resources of different types that aren't suitable, aren't available on just a mobile device. All right, so it's actually executed in the cloud. When you start executing in the cloud, you have all sorts of requirements related to latency. How responsive do you want that to be? Connected cars. Right? If you think about taking an automobile and connecting it, and applications that you might want to run on an automobile, a multimodal interface fits that as well. Right? So there's now speech interfaces for automobiles. Right? What's annoying about an automobile, you're trying to drive and manipulate your interface to all the electronics in your car now. Doing that via speech is also another type of multimodal interface. This is a translation app. So it allows you, it's a speech-oriented app where you can speak in one language, it goes off into the cloud, and does a translation and comes back in another way. Very high-intensive computational resources. You can't run those on a mobile device. And then there are other kinds of of multimodal interfaces. So this is a picture of a table that you might interact with colleagues on, a Microsoft Surface-like device. A lot of the way these are implemented now is through touch interfaces, but you can also do it using video, right? So if you have a video that's sitting, watching a person's face, watching their gestures, you can do gesture recognition and face recognition, all those type of things, in order to implement this kind of collaborative work. That also requires lots of resources, right? And so it's not as feasible to run it on the device. You'd maybe like to run it somewhere else, like in the so this is a pitch for the AT&T Watson engine. AT&T has a long history of doing research in speech to text and text to speech, and the Watson engine encapsulates much of what I talked about. If you're interested in using this for your mobile app, it's actually now available. They got APIs available to develop. What about other scenarios? Collaborative services. Well, I've sort of touched on this already. So this idea of a Surface device. You can imagine using this for collaboration, as I mentioned. If you do that, you have other challenges that the cloud infrastructure has to support. Now it's no longer just back and forth with a device, it's also about sharing a state. And of course, sharing the state, you may want more than two. You may have some arbitrary numbers. Right? So you want to be able to share that state for collaborative work, for example, and do that in a general way for the cloud infrastructure. This is intended to represent ambient technology. Ambient technology is something that is where you instrument a space with audio and video, but it's not like a telepresence room or something like that. It's a more informal kind of interaction space, right? So it's a different way of doing collaboration in a more informal sense. And so that kind of thing you would also like to support with the cloud infrastructure. And of course, I've already mentioned this, but gaming is another one. So if you think about these massively multiplayer online games, and the kind of requirement imposed on an infrastructure, take a first-person shooter game or something like that. The responsiveness that you're expecting, that you need in order to be competitive in the game, really imposes high, demanding requirements on the infrastructure. Right? This is wireless as well as wired, right? As well. So if we can do something like this, it'd be great, and do it on an infrastructure that we can reprogram. What's another one? Personal proxies. What's a personal proxy? Well, one example is just a virtual desktop. Right, so I like to tell this story. Gorama mentioned that I work a lot with people in Japan. I have a lot of visitors that come from Japan. And there are companies in Japan where you're not allowed to travel with a laptop that has a disk in it for security reasons. Right? And so these poor guys come to our facility and they're running virtual desktops to Japan. And the latency to those servers that execute that is so great that it's essentially useless. All right, so what if you had a personal proxy, a proxy that runs that virtual desktop that follows you, right? So that when they come from Japan to New Jersey, where I am, their proxy follows them, and their virtual desktop is running closer to where the end user is. Now, there's an interesting research problem there, because it's not just put it as close as possible. It's really more of a balancing act, because especially in the enterprise space, that remote desktop is also accessing corporate resources on the back end. All right, so you have to find sort of a nice place to do it. It's a nice optimization problem. What about generalizing this? So we have this concept called virtual individual servers. So now think of this as not just your desktop, but think of it as a personal proxy that stores some of your information, stores your preferences, and personalized to you. All right, so think about the speech technology I was talking about before. Speech recognition is much better if it's personalized to the speaker. Now you can do that by storing it in the middle of a cloud, in a massive data center. But if you have a proxy that follows you, you can incorporate that, encapsulate that within that proxy, that personalization aspect, and potentially do a better job. So I've been focusing on services that essentially are very latency-oriented, if you will. Responsiveness is a big thing. But there are other aspects as well that you would like a cloud like this infrastructure to have. And one of those is the location-based service. So if you think about it, as you're traveling around, there are certain scenarios where you want to produce data and consume data that's based on a location. The most obvious example are things like Foursquare, right? Everybody's familiar with those. I go to Yelp, I go to Foursquare, I'm here, I go, where are the restaurants around me? Now think about generalizing that. So there's a project that we have called Air Graffiti, which allows you to essentially do what the name says, right? So instead of painting real graffiti, it allows you to associate virtual data, whether it's text, audio, video, etc., with a geographic location. So you go through this whole process of associating data with a location, and then being able to retrieve it later if you have the right coordinates and the right authorization. So you associate text, pictures, music, video with the location, browse what has already been added to that location. So here's a screenshot of a mobile device, and this is a lab at AT&T called the Z Lab. And this is somebody associating a caption, graffiti, with that particular location. Now, there's all sorts of interesting challenges when you do this. How do you define a location? So there's this very robust underlying technology that allows you to define zones and overlapping zones that you associate this data with. But the property is, you by and large want to consume this data where it's produced or closely. So that's how you associate it with it. You can then look at different zones, different locations. So the Z Lab is the name of the lab, and you can look at the data that's been associated with that. You can view it from the top, so these boxes are actually different zones, and they can overlap and encompass one another. So you might define one zone to be this room, another one to be the hotel, another one to be the town, etc. Right? And you want to be able to implement this in a robust way. And this is an augmented reality view, right? So you can imagine wearing your glasses that are augmented reality glasses, and you'll see this. As I'm looking at you, I will see all the graffiti associated with this room. You know, things like, gosh, this Keynote is really bad. You know, stuff like that you might associate with this room, and I can see that if I have this augmented reality view of it. Now, the interesting part of this is that, you know, this is sort of flashy, it's a nice app, but the real difficult part is implementing the platform, the engine underneath, in a very scalable, robust way, so that you can define these locations and that you can handle things like, for example, automobiles. So you can imagine a connected car scenario where we're trying to define a scenario that provides me with location information based on where the car is. So that one's a somewhat different kind of thing, a location-based. And there's just a browser. So if you look at some of these scenarios, and I could go on for days with all these different scenarios. If you look at the properties, the observations about what these requirements are that you're talking about, you end up with this laundry list of things that are important going forward for these kind of cloud infrastructure. So mobility is big, and so that's sort of been implicit in a lot of the examples. That, you know, the way the industry is going, it's all about mobility and mobile broadband. So there's a lot of mobility devices and things like that we're dealing with. So the idea of offloading computation. Mobile devices are, of course, getting more powerful. But my thesis is they're never going to be powerful enough to run everything that you want to do. Right? Because the apps are an arms race. The app developers want to do more and more. And so you're always going to have this scenario of offloaded computation. And you want to run that computation in various places. Right? Along with this is this notion of thin client. So the diskless laptop example was a thin client. But you can imagine sort of the device space bifurcating into expensive devices that have a lot of resources and very thin, very cheap devices, where essentially everything is offloaded. It's cheaper, it's easier to manage, you know, it's a trade-off. But in that case, you really need some very special properties related to quality of service, dependability, things like that in your cloud infrastructure. Ubiquitous access. You really want it to be available whenever and wherever you want. Different kinds of connectivity. Wireless, across cell phone network, across Wi-Fi networks, across wired networks of different types, etc. And you can read some of them. Low latency and responsiveness, I think, is key for a lot of what we're talking about. Other quality of service properties. You certainly need dependability. You need availability and support for those and the kinds of services that we're talking about too. local consumption of locally produced data, heterogeneous resources. All the things that really go into making up an infrastructure. Okay, now given these, the question is, what should the infrastructure look like? All right, so an extreme cloud is our definition of a cloud infrastructure, and it has several characteristics. One is, as I said, it's ubiquitous. Right? You want it to be available, you want it to be across any kind of network that you might have, and be accessible from that. So you can see that from the picture. You want to be able to support heterogeneous resources. So you have this sort of tension. You want a uniform platform. But if you look at cloud computing platforms now, they tend to provide a fairly small set of capabilities. So you can define a virtual machine of 5 times. Right? And so if you go talk to the big data people, they say, that's never going to work for me. It doesn't have the characteristics that I need as far as memory, connectivity, whatever, in order to do big data analytics. So they're not going to use cloud computing. Right? So if I want to support those kinds of things as well, I need to be able to support heterogeneous resources in some way. And then my favorite, which is about enhanced properties and service support. So a lot of what I've been talking about has been about the responsiveness. Responsiveness as far as latency is concerned, being able to support applications on this general cloud infrastructure that you might not think of supporting building on a cloud infrastructure. Now, if we back up, right, cloud computing is just distributed computing. Right? I mean, it's just sort of the latest instantiation of distributed computing. So it's all about building a distributed computing infrastructure that has enhanced properties related to quality of service, whether that be latency, whether that be throughput, whether that be availability, and things like that. And as I mentioned, we'd also like to be able to support high levels of abstractions for developing, deploying, operating, managing these services. So what we end up with is this sort of tagline. So it's really about putting cloud resources, conceptually infinite cloud resources, into your device. Right? So if I pretend this is my phone, I'd like to be able to think of this abstractly as not a resource-limited device, but as a device that provides me a portal, or that actually has conceptually infinite resources available to it, as far as computation, storage, and connectivity. At locations. Right? So this location aspect, again, is very important, depending on the application. And so we want to be able to capture that in this infrastructure. Now, how do you realize this? Well, that's one of the research questions. So, our view, my view, is that you want to strategically locate your cloud resources in the network, making it possible to deploy new services that are responsive and location sensitive. What does it mean to deploy them in the network? So right now, if you think about cloud infrastructures, they're typically based on what I would call a relatively modest number of data centers. Right? 5, 10. AT&T has 38 data centers. I still consider that modest. Right? And so the trend has definitely been toward capturing and running cloud infrastructures in ever larger data centers, they're being distributed out for a lot of the reasons I've talked about, but it's really in a small number of data centers. So we started this work by looking at some of the things that AT&T has potentially as a competitive advantage. And one of the things that AT&T has is a lot of physical locations. Right? And so what we're looking at is, does it make sense from the point of view of providing properties in this cloud infrastructure, from a business point of view, to look at those locations, things like old central offices, things like networking, routing center, things like points of presence on the network. Does it make sense to locate general purpose cloud resources at a lot of locations in the network? And by a lot of locations, a research question is what that actually means. But if you think about taking and logically pushing the resources to the edge so that you can provide this location aspect, so you can potentially provide better latency, responsiveness, things like that. Okay, so what are the technical challenges in doing that? Well, the first one is what I just said. Where are you going to put these cloud resources in order to realize the properties that you want to support the kinds of services that we're talking about and services that haven't been envisioned yet? I mean, the scientist part of me wants to say, let's build an extreme cloud with such low latency and such low responsiveness that it enables new applications. Applications that people haven't even thought of yet. Of course, that's a balancing act. And so one of the research questions is, where are you going to put those cloud resources in the network? How many do you need? What are really the latency requirements? How good can you get? Especially if you're talking a mobility network. And is that good enough to run really demanding applications? So that's one research question. Another one is, how do you support these? How do you support a large number of data centers, potentially, smaller data centers, in a cost-effective way? It's much different if you're operating a 10 data center than if you're operating 100 or 1,000. Right? The trade-offs are much different. Scale is also a big issue. And many of these challenges relate to dependability and quality of service in general. So I haven't focused so much on those, but if you think about it, given the kind of properties and what I'm going to use these for, having an infrastructure that is highly available is critical. Being able to support the building of services to take advantage of that is critical. Being able to manage the resources that you have and to locate applications in this infrastructure to provide the responsiveness, for example, or other quality service properties, requires a lot more sort of automated type of process than you might have now. So what does our research program look like? This is a picture. Actually, it's very much in the spirit of what Stephen Yao talked about yesterday, right? This sort of adaptive model of what you're trying to do. So our research program is really all about building, operating, and using a large-scale, network-centric, highly decentralized cloud infrastructure. If you think about what the challenges are, a big one is about what we call the cloud control plane. Right? So the cloud control plane is all about optimizing use of available resources while ensuring that service constraints are met. Available resources here can include things like power, for example, energy awareness, things like that. You want to implement adaptive behavior automatically. You want to provide a monitoring infrastructure in order to do that kind of adaptation. And you want to provide enhanced provisioning and deployment capabilities. So if you look at this figure on the right, it's really about this adaptation loop, this control loop, right? So it's all about having an extreme cloud infrastructure. Sorry, I only have one pointer, so I can't do this. Extreme cloud infrastructure at the bottom, you have cloud services running on top, and you want to monitor and do some sort of optimization of that entire infrastructure, including the apps running on it, and then you want to deploy, use that for your deployment decisions, as well as adapting what's already running. So fundamentally, thinking about it as researchers, there's a very big, very challenging multidimensional optimization problem. Right? That's all about trying to optimize across multiple kinds of constraints, given your current situation and available resources. And to meet your service constraints. I don't know how to do it. I mean, we've done some research in this. It's a hard problem. And so it's something I urge people to look at if they're all interested in studying. There are lots of other things as well. So this terminology, cloud operating system, basically, you can think of that as exactly what it sounds like, which is what about the infrastructure that you have, and how does that interface with the end user? So one way to think about it is I have my mobile device, right? You can view it as part of the cloud infrastructure. If you want to take that to an extreme case, you might run applications on it. You know, some sort of peer-to-peer kind of I'll share my resources if you want. But even if you don't do that, and you don't share the resources on your device, you have to view it as being incorporated in the larger cloud infrastructure and have it be integrated in some way through essentially an operating system technology in order to really do this in a seamless fashion. So that's a research challenge as well. And then all of these novel services and applications are certainly part of the research that goes into this. And in fact, the research program that we're developing is really going to look at core technology, but we're going to have a couple of drivers as far as applications, where we'll take an application, we'll pick a couple of applications, and sort of drive them all the way from top to bottom, end to end, to see what we can do. Those are still being decided. So what I want to do in the remaining time is sort of give you a flavor of the kind of research that we're talking about. This is really about projects that predate extreme cloud, but they were really part of the input that went into how we defined it. And so you can view them as predecessors to the Extreme Cloud Initiative, but very much in keeping in the spirit. So Tropic is about cloud orchestration. All right, so this is very much the control plane aspect. And I'll talk about this. Transactional manipulation of compute, storage, and network resources. Mistral is work that we've done on this cloud control plane and this optimization problem. So I'll talk a little bit about that. And then Pipe Cloud is about cloud-based disaster recovery. And cloud-based disaster recovery, another way to do disaster recovery, it's really about providing infrastructure support to run applications that are more highly available. So don't think about it as disaster recovery. Think about it as providing a layer that you can run applications on that, in the event of a failure, will keep running in some other data set. Right? So that's really what disaster recovery is all about. And so I'll talk about that. So Tropic is all about transactional cloud orchestration. It was done with the 2 people at AT&T, the 3 people, 4 people, first 4 authors at AT&T. This was done in conjunction with people at the University of Pennsylvania. And in fact, it's largely a PhD dissertation of the first author there, Changping Liu, who's now at AT&T. But Tropic is all about providing orchestration. Orchestration is all about provisioning of applications, configuring and decommissioning the virtual resources across a distributed set of physical resources. So think about it this way. If you're running a general purpose cloud infrastructure, you're going to want to deploy these applications and potentially move them. What's the mechanism that you use to do this kind of thing? Now, if you're familiar with virtual machine technology, you might be aware that they provide the ability to move virtual machines at runtime. That's not enough. And in fact, it's largely confined within a data set. One of the key points of this research is to note that that's only the starting point. That there's really much more that's required to do this in a seamless fashion. And a lot of it is networking. Right? That's one of the things that's sort of under the covers, but as a networking company, that's something that's very visible to us. Right? Is how much networking configuration do you need to move an application or part of an application from here to there. Okay, so let me talk about Tropic a little bit. So what are the challenges here? One is the seamless integration of cloud resources and VPNs. So a lot of what we're talking about here is for enterprise customers. And enterprise customers have their corporate VPNs, virtual private networks. And a large problem or a challenge in this is to provide cloud resources that are actually on their VPNs. Right? So there's a solution we have called CloudNet. There are papers about that. I'm not going to talk about that part of it. So we're going to assume that that's been solved. But then we have the resource provisioning. And the problem is the resource provisioning tools that are there now are very tightly coupled to the individual vendor devices. This is especially true at the network level. So if you look at what tools are provided by Cisco, Juniper, by those, they're very specific to that company. Right? And what we'd like to do is sort of raise the level of abstraction so that we can do things at a higher level. So that's one of the challenges. And because of that, we have no interoperability, and it's a very low-level control interfaces, especially at the network. So Tropic is a platform for defining, provisioning, and managing the cloud services. So think of it as you have your cloud infrastructure, including the network. You have your apps that you're running on it. How do you manage this holistically as a single unit? And the key is we want to support the migration, mobility of services across the network that enable things like gaming, for example. All these examples I talked about where people are moving, or the locus of activity is moving, we may want to move these virtual machines and their connectivity. So Tropic provides the ability to define cloud services that are robust in a transactional sense. So one of the big contributions of Tropic is that it provides transactional semantics for these configuration changes. So it allows you to recover from misconfigurations, device errors, etc. in a seamless fashion. It's safe in the sense that it enhances, enforces service and engineering constraints. I won't spend a lot of time talking about that. But it's also highly available, the Tropic infrastructure itself. All right, so as we talked about, in order to do an extreme cloud with the kind of properties we talked about, the infrastructure itself has to be highly available. And they've done that with this Tropic infrastructure. Okay, so here, let me give you a view of what Tropic is. So at the bottom are your devices. Right, so you have compute devices, storage devices, network devices, and you have your devices and APIs. As you move up, what Tropic provides you, first of all, is this physical layer abstraction. So they define a physical data model, and they provide that, so they abstract that away, and provide that through this queue interface to a high-level logical data model. Right, and so what you have coming in at the top are orchestration requests. And I'll give an example, but moving a virtual machine would be an orchestration request. Right? And so those requests come in at the top, and using the logical data model and the physical data model underneath, it provides you the ability to make these changes. And so we have the logical and the physical layers. We have replicas. We have controllers at the top, which is organized in a leader-follower fashion. We have workers that are replicated at the bottom. And we have a transaction manager here, this controller at the top, that essentially does a lot of the scheduling and the concurrency control and things like that to do the changes. The components that are replicated for high availability are the ones that are highlighted. So we have queues, distributed queues, we have multiple controllers, we have replicated persistent storage. Okay, now what can you use this for? So let's look at this scenario. Let's say it's a gaming scenario. So we have two data centers, one in Hong Kong, it runs in Michael's house, and another one in New York, right? And we have a community of gamers that are using this infrastructure in order to online game. So you can imagine a follow-the-sun kind of scenario where during the day in the US, most of your activity, or actually if it's gamers, you have to maybe adjust it, so maybe it's at night or whatever. But you're likely to have a preponderance of the activity being in the US at a certain time. All right, so this is set up so that, in fact, the server is going to be, the primary server is going to be sitting in the US. All right, so we have there the virtual machine that's implementing the game, and the networks are set up to route the traffic to that no matter where you are. So that's your scenario. Now, as the day or the night goes on, the preponderance activity might change to Asia. All right? And so we have a scenario like this. And given this kind of scenario, it might make sense to move that gaming server to Michael Liu's house. Right? And so to do that, you want to do that. But as I said, that's only part of the problem. Right? You also have to solve this problem. If you don't do anything else, this is how your traffic is going to be routed. Right? And this doesn't solve the problem. All right? And so to do this kind of thing, they told me how many like commands it takes. It's, hundreds of commands at the switch level to make some changes. So what you really want to do is have it be like that. Right? And so the steps that you have to go through to do that are what Tropic will do. It will orchestrate those in a transactional fashion so that you aren't going to get stuck in a middle scenario where some of those commands have been executed and others haven't. So either everything's going to have been moved, including the network, or they won't. All right? So you get these transactional semantics, it can roll back, it has a collection of engineering constraints to make sure those constraints are going to be satisfied. Things about, is there enough space on the servers, the destination servers, is there enough networking capacity, things like that. So that's what you end up with in what Tropic is, it's the mechanism to allow you to do it. Okay, so summarizing about Tropic, it really addresses the control plane issues of assigning virtual to physical resources and orchestrating those changes. Provides a high level of abstraction. That's one of the challenges in this work, is that the level of abstraction right now in cloud computing is really a fairly low level abstraction. Right? And so raising that level of abstraction is one of the challenges that I think we have to deal with. So in the case of Tropic, it's a data model to deal with heterogeneity of resources. There's actually a domain-specific language in there that allows you to specify constraints and to make sure that those are satisfied. The transactional execution semantics that I talked about. I didn't give you an experimental result, but they've been able to show pretty convincingly that this scales. And a lot of it is, transactional, it's all about providing the semantics while still allowing high concurrence. And Tropic will do. So one interesting thing about this is, I don't know if you're familiar, there's this open source thing called the OpenStack, which is essentially an open source stack of cloud software. So this is currently being good now, and my department is actually a core member of the OpenStack team, and some of these features are currently being rolled into the OpenStack open source software for running cloud systems. So Rackspace, for example, is one of the chief proponents behind and advocates behind OpenStack. Tropic is all about the mechanism, about moving things in a cloud infrastructure. Mistral addresses the complementary problem of the policies. When do you want to make changes? And what should those changes be? Right, so you can think of this as implementing this control loop and managing resources in the cloud to do this multi-constraint optimization. In this case, what we did is we were looking at multi-tier enterprise applications. So things that have a front-end web server and an application server and a back-end database, for example. Looking at a cloud infrastructure that executes many of these kind of multi-tier applications. And what we wanted to do was optimize across a number of criteria, while still meeting the SLAs, the service level agreements, as far as response time is concerned for these applications. So what you'd really like to do is look at this holistically and take the virtual machines and place them in a way that maximizes the resource utilization. So one of the motivations for cloud computing, right, is that server utilization is 20% normally, 10%. It's very low. Cloud computing, in theory, allows you to up that to 80, 90%. So we want to be able to do that with all the savings that entails, while still meeting the response time constraints that we have, and potentially other constraints. So what this did is it looked at it as a optimization problem. And like I said, I'm not going to go into the details, but this is the architecture. So it's all about, in this particular solution, doing offline experiments to construct models that allow you to predict what the effect of a given change in your configuration, in your resource allocation is, on the response time, that's the LQN model there, on the power, and on the cost, which is the cost of the impact of moving things. And you end up with a controller in the middle that's based on those models. And based on the inputs we're monitoring, you'll make control changes that hopefully will increase your utilization while maintaining those constraints that we've seen. And so this is a very unfair picture because I'm not going to tell you anything about it, but obviously this one is the best. That's the top line. But basically this is a workload a workload that we took and looked at different controller policies, different ways of doing this kind of control. And basically what the other ones are what you get if you only optimize, two of the three constraints we were looking at here. Right, so the value that we get is that, and the utility function captures how good your solution is. And that's what captures things like meeting the constraints as far as response time is concerned. And addresses the control plane issue of optimizing the resource utilization to adaptive actions. So let me spend the rest of my time talking about pipeline. But this is about disaster recovery as a cloud source. This is done by K.K. Ramakrishnan and his colleagues. A lot of our work is done collaboratively with universities. So this was UMass. The Mistral work was done with people at Georgia Tech. If you look at disaster recovery as an enterprise application, as something that you sell to an enterprise customer, it's really about providing these services to support business continuity by allowing applications to rapidly come back online after a failure. Now, disaster recovery tends to imply what the name says. It's not just failures, it's disasters. If you lose a data set, for example, completely. You have a Northeast power outage. Gee, I wonder where I got that example. For 5 days, what do? Current disaster recovery services are actually quite expensive. They're very custom. And they either come at a very high cost by doing a very synchronous kind of replication, or very weak guarantees on the amount of data links. So if you look at async versus sync, replication of these applications, you have this kind of fundamental trade-off. And you end up with what's called a large recovery point objective. So a recovery point objective is basically the amount of time it takes to restart the operation after a failure. So a small RPO is a good thing. Right? So what this research was doing is looking at using general cloud computing platforms to do disaster recovery that allow you to minimize the cost, lower the cost, and have a small RPO. So how would you use the cloud? Well, this is the way disaster recovery is done typically now in enterprise. So you have your primary data center, you replicate it, you have a private backup site, where the synchrony is done at a low level. You're replicating disk writes, essentially, right? It's very synchronous. And so you end up switching to the backup site after the disaster. So you can have this kind of solution, but it's a very carefully engineered, very sort of non-shared solution. What you'd really like to look at is, suppose you could define a public disaster recovery cloud. Right? So rather than use a private backup site, suppose we have a public site. One of the characteristics of disaster recovery is you don't really need very many resources until you get to the disaster. So you can imagine having a smaller number of resources here in the public disaster recovery cloud and using them across multiple companies. So the multi-tenancy aspect of clouds. The challenge is, as this is supposed to indicate, you have less guarantees if you're talking about a public cloud. So think about what Extreme Cloud would bring to this course. So what you want to be able to do is support disaster recovery for multiple enterprises in a public DR site. And so a lot of the work in this is about using the cloud public DR site to reduce the cost of it and improve the level of service. And the way they do that is by having a very low-level shim that sits in the virtual machine that does this kind of replication. So here's what you end up with. You have your primary site, you have your cloud site on the right here, and you're doing this replication across the wide area network. During non-failure modes, you're replicating the state, and as I said, you can statistically multiplex it on the disaster recovery site because it requires actually very few resources to apply these changes. And you want to do the rollover only when necessary, and at that point you can use the cloud elasticity to ramp up the amount of resources you give to running that application in the public cloud site. So this is how they do it, and I'm not going to go into the details because that's provided in the paper. But basically, they end up pipelining the writes. That's where the name pipe cloud comes from. So you end up treating the virtual machine as a black box. Right? These are enterprise customers. We can't really instrument their applications because we're the service provider. So you end up not modifying the application, but you end up intercepting at the hypervisor level all the I/O and essentially streaming. It enforces a total ordering, but it does it in a way by delaying the responses so that you get this kind of pipeline semantics. And so what you end up with in this, glossing over 90% of the details, is a low RPO. In other words, you're not constraining the concurrency of the application much because you're allowing it to proceed, but you still minimize the recovery point objective based on where your recovery line is in essence. And so what you end up with is a cost-effective cloud-based disaster recovery strong guarantees. So as I said, for this talk, I'd really like you to think of this as providing a level of abstraction to application to provide higher availability. So if you think about it in the extreme cloud terms, it's really about providing abstractions or services to an application to enable application writers to have higher availability. In this case, it's transparent to the application writer, right? But it's a level of abstraction, raising the level of abstraction to provide this higher level of service. And it relies on and exploit the capabilities of the cloud infrastructure, right? The fact that you can elastically increase and decrease the resources especially is a big part of it. And it really demonstrates, in my view, a compelling approach to realizing enhanced properties for applications that use the cloud. You provide a layer, provides disaster recovery, provides higher availability, and now you can build your application. Okay, let me go ahead and wrap up. So just to recap, in Extreme Cloud, it's a work in progress, and I'm welcoming questions and feedback, but it's all about providing a cloud infrastructure to support new types of services that have more demanding requirements. So it's ubiquitous, supports heterogeneous compute storage and network resources, provides enhanced properties and service support, and realized through a highly decentralized infrastructure. And you can see there that it really is about the abstraction of more resources and devices than you have on the device. And those of you that are old as me will remember that we've been talking about a true computer utility since at least the 70s, probably before that, the 60s. Right? So this was a big part of MIT's Project Math, was viewing computing as a utility, in much the same way you would view power, water, those types of things. We're almost getting to that point. Right? It's not seamless now. It's not like you can plug your computer in, but we're getting there. And I think with this kind of cloud computing infrastructure, you're actually getting pretty close to a true computer utility and all the potential advantages that might allow. Okay? With that, I'll thank everybody, and there's our current Rethink Possible phrase. Thank you very much.
I had a question. You mentioned about strategically locating resources, and then you also said general purpose resources would be located everywhere. So, can you elaborate a little more on what you exactly mean by strategic location of resources?
So statistical location? So it's really about statistically multiplexing the resources that you have, right? So one of the premises behind cloud computing is that you'll have a variety of applications with different resource requirements. And that by statistically multiplexing those on the same infrastructure, you can get a higher utilization. Right? So that's what I meant by that. It's not really related so much to where those resources may be, but you need to be able to compute and calculate where to put applications, meaning how to assign them to the platform and what resources to give to them. And that will involve the statistical multiplexing and understanding the behavior of the applications you have running on your application, on your platform.
Okay, thanks. I had one more question. In the DR as a service part that you talked about, you said that network packets would possibly be on hold till the previous disk writes are committed. So is it possible that you were at the point of a DR situation and you did not have the disk writes committed, and then you had this network packet which was actually saying that a DR is expected to happen now. But because the disk write did not commit, your actual request for a DR came in much later than required. So wouldn't that kind of delay the actual DR operation from happening?
I think the answer is no. So obviously I didn't go into a lot of details. Plus, it's not even my work, right? So I don't know, a lot of the details. I would encourage you to look at the papers. But the delay that I was talking about is really not a delay in applying the disk writes. You pipeline the disk writes, and you delay the responses to those disk writes, the acts, back to the original site in order to make sure that they're committed. But by pipelining them in the infrastructure, you can reduce the amount of time that you have to wait for those things.
Thank you very much for an interesting talk. In your slides, and I see infrastructure and networks, and I'm working the network side. So my question is, what's your view of optical networks in the cloud?
Optical networks?
Yes, thank you.
Well, certainly optical networks are a big part of an infrastructure, a modern telecom infrastructure like AT&T has. I think it's a little bit of an orthogonal problem that it's one of, so if you think about trying to manage and allocate resources for the services or the applications that you deploy, what you need to do is make calculations about what the latency is and things like that. And whether you have an optical network and where it is going to impact what goes on. So it certainly impacts those. But the reality is, especially in the mobility network, that the air part of it, right, the wireless part is really the biggest constraint on responsiveness. All right, so I haven't done the calculations, but it's a big part of it, and so the optical networking is certainly pushed out close to the edge, but I don't know if there's a big advantage in argument that needs to be pushed out any further than it is. So I think it's a little bit of an orthogonal.
So over the last probably 30, 40 years, we sort of went from a centralized system, we went then towards a distributed system. The solution was then a fully distributed environment. That was found to be a nightmare. We went back to centralized systems. That was found to be too constrained because people want freedom to do whatever they want to do. We then had the grid, which is a centralized system. We're back to decentralized systems. You're proposing another centralized system. Cloud is centralized. It's just a load of computers. Okay, I'm giving you my data. Distributed systems was we control our own data. Everything has ended up as a hybrid between centralized and decentralized. Cloud is just another centralized system which has failed over the last 20 years. I don't really see why. I'm not willing to give, I don't think anyone's willing to give all their information to a central point. And we're going to end up back into a hybrid solution.
So let's be clear, when we're talking about centralized versus decentralized and the way you're referring to it, you're really talking about the authority over the infrastructure.
But that's always been the battle between centralized.
Right, and so it's a very decentralized physical infrastructure that we're talking about in the extreme cloud, right? And that's the way it is now. Any cloud computing infrastructure is very decentralized physically.
Data is centralized.
It doesn't have to be. It can be out to the edges as well, and that's one of the things I didn't talk about. But the question of how do how much authority the user wants to give whoever's the infrastructure provider, that's really the question. And I agree that that's that's something to be explored. And in fact, some of our security and privacy-related research is all about providing, for example, more control over the data that you store in the cloud by providing in your personal proxy the opportunity to do that. Whether you're comfortable trusting AT&T to implement the policies that it says, or any infrastructure provider, that's really the question, right? And so I'd like to think that AT&T is one of the more trustworthy organizations with a 150-year history of protecting user data, back through the telephone. We've had to do that for years and years. But you're right. In that sense, this question of the control of the data, the control of the being able to trust the utility with your computing needs is really fundamental.
Thank you. We have two last questions.
So this is a question on behalf of the graduate students and maybe the young faculty of the ISSRE software reliability engineering community. The question to you is, what would you ask this community, the software reliability community, the top 5 research problems they need to solve in the next 5 years, or maybe 2 years? You set the timeline, but you've been an academic, now in industry, so you bring a perspective that they would not easily have. So could you just list, and you can take your time to think about it.
I'll come back next year.
We'll give you 30 seconds, and then.
Well, I'm not going to list 5, right? So it's my prerogative as the keynote to ignore the question, right? But to me, sort of a lot of the traditional reliability engineering problems are still there. There may be harder. I think, so I'm a little bit, I don't know if I want to say cynical, but what we've essentially done with cloud computing is add yet another layer of software, right? And it's a hypervisor level. And whenever you add software to your stack, you have more variables, more degrees of freedom, more opportunities for reliability problems, right? And so any research that allows you to argue about this deep software stack, and not just, I think, to me, over the years, one of the hardest problems has been this deep software stack, and being able to argue about end-to-end properties, including reliability, because you have this deep software stack. By adding a hypervisor and virtualization, you just add into that stack. So to me, that's one key thing, is dealing with this software stack and its end-to-end properties. The other aspect of cloud computing that's critical is quality of service properties beyond, that include things like timeliness, right? So arguing about more than just the traditional reliability properties, right? That's an important thing as well. A third thing is this kind of infrastructure, in the most extreme case, shall we say, in my own vision, is a very dynamic infrastructure. Right? If I had my druthers as a researcher, I'd be moving virtual machines around willy-nilly in order to optimize. Right? Doing that in a safe way, doing that in a way that I can make sure I meet the properties, I think that also impacts the kind of things that happen in this community. That's 3. Is that okay? Good, right? 2 more. Don't have to.
Just last question, because we have to.
You mentioned MIT time sharing network. Let's go back. 1960s batch processing, 1970s time sharing, 1980s the PC came in and time sharing sort of went away. Now, what about the possibility with the super personal computer? A lot of the advantages of cloud will go away. Now, I'll debunk 2 easy ones. You're in your car traveling, of course. That doesn't work. You want a collaborative research among a number of people in different locations. That doesn't work. How about some of the others? Will an extreme PC cut into the opportunities of cloud?
I think the answer is mostly no. And I think the answer is mostly no because the connectivity part of it, the collaboration part of it, is really, in my view, going to be the driving application for a lot of what we're talking about. So, yes, super PCs are, if you're sitting at your home with a super PC, you have less need for resources in the cloud. Great. But I think the connectivity is always going to be a requirement. You may be using that super PC to do gaming, right? And so that the shared state, right? Whenever you do collaboration, including gaming, you're going to have a shared state of some sort. And implementing that shared state is something that's really sort of a cloud, network-centric kind of view. So I don't think it's going to solve the problem. It may simplify something.
Thank you again. Thank you for the audience for all the questions.